So in the last session, been talking about the properties of ideals in the ring of polynomials. And we also compared the ideals in the ring of polynomials is almost identical to the ideals in the ring of integers. So we'll do some more properties of ideals. Before going there, just want to recall one result here. Between fields and integral domain. Any field is an integral domain. We know this, and we already use this result in a couple of places. But when can an integral domain become a field? The result is that a finite integral domain is a field. We are going to use this one to study one more property of an ideal. So we have two results we already established earlier. One is M is maximal if and only if M is maximal in a commutative ring R if and only if R by M is a field. And the second property is N is prime in R if and only if R by N is an integral domain. And we also know that because of this result, we also know that a maximal ideal in a commutative ring R is also a prime ideal. That is because every field is an integral domain. So if you are going to use the second result here, we can say that if R is a finite commutative ring with unity, and N is a prime ideal, then what happens here? N by R is a finite integral domain. By the second result. So if it's a finite integral domain, then it's a field. That implies R by N is a field and that implies n is maximal. So for a finite commutative ring, maximal ideal is always prime ideal and prime ideal is always maximal ideal. So there is no difference in case of a finite commutative ring. So the fourth result is, in a finite commutative ring, every prime ideal is a maximal ideal. This is another result, fourth result. So let us see what happens, the relation between the prime and maximal ideal in the ring of polynomials. We know that every maximal ideal is a prime ideal, so that direction is not a problem. Let us assume that there is a prime ideal in the ring of polynomials. So let n be a prime ideal in f of x, where f is a field. And we know that any ideal in f of x is principal. Since A is an ideal, n is an ideal, implies n is equal to the principal ideal generated by P of x for some P of x in f of x. Our aim is to find out the properties of this polynomial, whether it is reducible or not. If it is irreducible, then of course n will become a maximal ideal. So we need to find out whether P can be an irreducible polynomial. So what happens is, we will assume that P of x is reducible. If it is irreducible, then we have already the result. So we are assuming that it is an irreducible. It is irreducible. So that implies P of x equal to g of x times h of x for some g of x comma h of x in f of x. Since n is a principal ideal generated by P of x actually belongs to n. And that implies g of x times h of x belongs to n. But n is a prime ideal. In a prime ideal, if the product is in n, either the first element or the second element is in n. So that implies either g of x is in n or h of x in n. Why? Because n is prime. So n is actually generated by P of x. So that means g of x equal to P of x times q1 of x, or h of x equal to p of x times q2 of x for some q1 of x, q2 of x in f of x. But this is not possible because we already assumed that p of x is equal to g of x times h of x. So, the degree of p of x is greater than or equal to g of x, and the degree of p of x is greater or equal to h of x. So, this is not possible. This is not possible because we assumed that p of x is equal to g of x times h of x. So we are arriving at a contradiction. That is because we are assuming that it is reducible. So this is a contradiction. That implies p of x is irreducible. That implies n is maximal. So in f of x, the ring of polynomials over f, every prime ideal is also maximal. So we will do one more property of the ideals in the ring of polynomials. So let f of x be a ring of polynomials over f, over the field f, and we take two elements here, f of x comma g of x in f of x. Then let's assume that f of x divides g of x, and that implies f of x divides g of x means f of x is a factor of g of x. That implies g of x equal to f of x times h of x for some h of x in f of x. And this implies g of x belongs to the principal ideal generated by f of x. That is the definition of principal ideal. So if f of x divides g of x, then g of x is in the principal ideal generated by f of x. Now we'll assume the other way. Assume that g of x is in the principal ideal generated by f of x, and that implies g of x is equal to f of x times h of x for some h of x in f of x, and that implies f of x divides g of x. So the result is in f of x, the polynomial f of x divides g of x if and only if g of x belongs to the principal ideal generated by f of x. This is if and only if. F of x divides g of x if and only if g of x belongs to f of x. We also do a small problem. So let A and B be two ideals in a ring R. And we are going to define another set collection of elements A plus B such that A belongs to A and B belongs to B. Then our aim is to find out whether A plus B is also an ideal. If A is an ideal and B is an ideal, then we need to find out whether it's an ideal or not. So, how do you prove that a subcollection is an ideal? The first step is we should prove that, need to prove that A plus B is a group or is a subgroup. Is a subgroup of R with addition as the binary operation. How do you prove that this is a subgroup? We need to find out the identity belongs to A plus B. Every element has an inverse and it is closed. So 0 belongs to A plus B because 0 plus 0 is equal to 0. This actually I am taking an element from A, this I am taking an element from B. So addition is already there. What about inverse? So for an element A plus B in A plus B, the inverse, the additive inverse is minus A minus B, or you can say minus A plus minus B. And this is definitely in A plus B because minus A belongs to A, minus B belongs to B. So that is also done. So we have identity and we have inverse. Let's say it is closed under addition. How do you say it's closed under addition? We will take two elements, A1 plus B1 and A2 plus B2 belongs to A plus B. And that is equal to, that implies A1 plus B1 plus A2 plus B2 is equal to A1 plus A2 plus B1 plus B2. Why? Because addition is always commutative in R. In this case, I am not insisting that R is a commutative ring, but still this is true. And this belongs to A plus B because A1 plus A2 belongs to A, B1 plus B2 belongs to B. So it is also closed under addition. So this is a sub. So A plus B is a subgroup of R. Now we need to prove that this is a subring. In order to prove that it is a subring, we need to prove that multiplication is associative and multiplication is distributive over addition. So let's first find whether it is associative. Multiplication is associative. So take three elements, A1 plus B1 times A2 plus B2 times A3 plus B3. These are three elements from A plus B, and I am actually going to see whether it is associative. See, this element is from R, this element is from R, and this also from R. And R is a ring. So we can always write it like A1 plus B1 times A2 plus B2 times A3 plus B3. Because these elements are actually from R. So it actually comes from R. The associativity is coming from R. So multiplication is associative in A plus B. Now we'll see whether it is distributive or not. So we'll take A1 plus B1 plus A2 plus B2 over A3 plus B3 multiplied by A3 plus B3. Again, it is these are all elements from R. So we can always write it like A1 plus B1 times A3 plus B3 plus A2 plus B2 times A3 plus B3. So multiplication is distributive over addition. So this is a subring. And the final thing we want to prove that it is an ideal. How do you prove that a subring is an ideal? If n is a subring of R, take any element from here, then multiply that with n, and that should be a subset of n. We'll take the same example here. So we'll do, let R belongs to R. So R times A1 plus B1. A1 plus B1 is an arbitrary element in N, is equal to RA1 plus RB1, and this belongs to, so this belongs to A plus B, because this belongs to A and this belongs to B, because A and B are ideals. And that implies R times A plus B is contained in A plus B. And that implies A plus B is an ideal. So I'm going to end the session on principal and maximal ideal with two more examples, or probably you can take it as two more problems. Very simple problem, but I just want to go through that before we complete this session on prime and maximal ideals. So consider Z3 of x. This is a collection of ring of polynomials with coefficients from Z3. Okay? Then I want to find out. So let's take this quotient here, Z3 of x over a principal ideal generated by x cube plus x plus an arbitrary constant c. X cube plus x square arbitrary constant c. And I want to find out what would be the value of C if this quotient is a field. If you want to make this quotient a field. This is the base ring, and I am taking a quotient, and this is actually the principal ideal generated by this polynomial. This polynomial is definitely in here if C is chosen properly. But any element, any value of C from Z3, this may not be a field. So we want to find out the value of C such that this quotient becomes a field. So this is a field only if x square plus x cube, sorry, this is a field only if the principal ideal generated by this is maximal. See, the result is like this: R by M is a field if and only if M is maximal. So this is the result I am going to use here. So if you want to make this as a field, this has to be maximal. And the principal ideal generated by E is maximal only if x cube plus x square plus c is irreducible in z of x, C3 of x. C3 of x. So we need to find out the values of C such that this is a irreducible polynomial. So what are the possible values of C? C has to come from Z3. The possible values of C are 0, 1, 2. So the possible polynomials are f of x equal to x square x cube plus x square plus 0. This is when c is equal to 0. When c is equal to 1, f of x will be x cube plus x square plus 1. When c is equal to 2, f of x is equal to x cube plus x square plus 2. How do you show that this one of this is reducible or not? If you put the values of x from Z3, it should not vanish. If you vanish, then it is reducible. For example, here f of 0 is equal to 0. That means f of x is reducible. Here f of 1 is equal to 0. So 1 square, 1 cube 1, 1, 1. 1 plus 1 plus 1, 3. 3 in Z3 is 0. That means f of x is reducible. So in these two cases, f of x is reducible. Let's see what happens here. Here if you put 2 here, sorry, if you put values 1, 2, 0, 0 is actually f0 is 2, f1 is 1 square, 1 square plus 1 cube. So 2 plus 2, 4 is equal to 1, and f of 2 is equal to 8, 4, 12, 14, that is equal to 2. So if you put any values for x, this is going to be an irreducible polynomial. Meaning this polynomial will not vanish. That means this is an irreducible polynomial when c is equal to 2. So the answer is, when c is equal to 3, this quotient x cube plus x square plus c is a field. This is the way you should prove it. Next example is going to be similar, but I will not do all the steps. I am going to write it and give the answer. So you can develop the same kind of argument to arrive at the result. So we are going to consider here z5 of x, and we are going to consider z5 of x over, what is that, x square plus cx plus 1, the principal ideal generated by x square plus cx plus 1. So it's only if is a field. So value of c such that this quotient is a field. So the c is coming from either 0, 1, 2, 3 and 4. Or you want to write it like, so this is a field if and only if x square plus cx plus 1 is maximal. Implies x square plus cx plus 1 is irreducible in z of x, c5 of x. So values of c are 0, 1, 2, 3, 4 and 4. So when c is equal to 0, c is equal to 1, c is equal to 2, c is equal to 3, c is equal to 4, the way the polynomial is x square plus 1, x square plus x plus 1 is equal to x square plus 2x plus 1, x square plus 3x plus 1, x square plus 4x plus 1. So these are the possible polynomials for this quotient to be a field. So what we need to do is we need to find out the values of c such that this is irreducible. The answer is when c is equal to 1 or 4, that is x square plus x plus 1 and x square plus 4x plus 1 are the only irreducible polynomials in C5 of X. So the values of C are 1 and 4 for C5 X squared plus Cx plus 1 is a field. To be a field. To be a field. So that completes my session on the prime and principal ideals. Okay, we'll continue with the next chapter in the next class.